The Lewis dot symbol is a graphical representation of an atom or an ion and its valence electrons. So if we have sodium, sodium is Na, and its valence electrons are in S1. There's one valence electron. We show that with a Lewis dot symbol by using the chemical symbol for sodium, Na, and then we put one dot. That dot represents the valence electron for sodium. Calcium has a valence electron of S2. So there's two valence electrons, and that's its configuration. It's in S2. Now, when we put dots for calcium, we separate those dots as far apart as we can get because electrons all have a -1 charge and they want to get away from each other. So we separate them like this. Boron, which is the next main group element in row 2, it has an S2P1. So there are 3 valence electrons for boron. We show that by putting 3 dots around the chemical symbol for boron, B. Moving over, we then have carbon. Carbon's chemical symbol is a C, and their valence electrons are S2P2, so there are 4. So for carbon, we separate those 4 valence electrons by putting a dot on each face. If we imagine each of these chemical symbols as being in a square, then there are 4 faces here. Now, as soon as we get to nitrogen, now we have to start pairing our electrons. So nitrogen has a valence electron configuration of S2P3, and this is a 2s2, 2p3, but I'm trying to use the generic here because this actually goes for all of the elements in the column. So when we have nitrogen, we're going to use Hund's rule that all orbitals get 1 electron before anybody gets 2. So this is nitrogen's Lewis dot symbol. For oxygen, we have S2P4. Oxygen's chemical symbol is O, and we end up having 2 pairs and 2 loners over here, 2 unpaired electrons. Then we have fluorine, which is, oh, I put that in the wrong spot. We have fluorine, which is our halogen in row 2. Fluorine is F and has a valence electron configuration of S2P5. So we have 7 valence electrons around fluorine. And then our noble gas is neon in row 2, and it has a valence electron configuration of S2P6. And then we have a full octet, or 8 electrons around neon, and we show them this way. All of their electrons are paired. So these are the Lewis dot symbols for the second row on the periodic table. And the dots represent those valence electrons found in the electron configuration. Now, when an atom gains or loses electrons, it becomes an ion. When an atom gains electrons or becomes negative, like fluorine, plus 1 electron is going to become the fluoride ion. We show that by increasing the electrons around it, putting it in square brackets, and giving it its charge. Now that is called an anion. When an atom gains an electron, it has 1 more or 2 more electrons than what it came in with, it becomes an ion. Now when you have a metal, say sodium, sodium wants to give up its electron. So sodium minus an electron becomes Na+. Now we can show this ionic transfer with our Lewis structures. I said structures, I meant dots, with our Lewis dots. And how we show that is we start with our atoms. So here's my sodium, and I'm going to react it with fluorine, and that will form my sodium cation, or positively charged ion, and my fluoride anion. So I put all of the electrons around the fluorine, square brackets, and a minus sign. That's how we show it for an ionic compound. Now, most of the time when we're looking at Lewis dots, however, we're really interested in the covalent compounds, those that share their electrons. And this is going to be between two or more nonmetals. So let's just start with hydrogen. Hydrogen comes in with 1 electron. And when it hits the sweet spot with another hydrogen atom, what happens is there is a sharing of these electrons. And as these electrons share with one another, because hydrogen wants a duet, it only has that one s orbital. And that s orbital is full when there are 2 electrons in it. There is a sweet spot, a distance between these 2 nuclei, where they will share these electrons. And when they share these electrons, then we have what is called a covalent bond. So we have these 2 electrons here, and we show that with what's called a Lewis structure, where we draw a line between the 2 atoms. One line is 2 electrons, one line is 1 bond. Now specifically, this is called a single bond. And I'm just going to do a little name dropping here because it will help for later. This single bond is called a sigma bond. So single equals sigma. Now we can do this with many of our atoms. So for example, if I take chlorine, which is in period 3 and it's a halogen, and because it's a halogen, it's like fluorine and it has 7 electrons. And when it hits its sweet spot, because each sweet spot is going to be a little bit different, it will share its electron. Now I'm going to I really should change the color here. So you can see how each atom brings an electron. So when they get close enough, then they share these electrons. And once they share those electrons, then what we have these pairs around. These are called lone pairs. Then we're going to share, and these other lone pairs stay here. Now, once we're sharing those electrons, what we've done is we've satisfied the octet. So this bond is considered, the electrons in the bond are considered around that chlorine and around that chlorine. So you see we have 8 electrons around each of those atoms, and that satisfies the octet rule. The octet rule states that an atom will gain, lose, or share electrons to have an octet, or 8 electrons around it. Again, we have formed a single bond, and that single bond is made up of 2 electrons, and we also call that a sigma bond. Again, that's something that will pay dividends in a later video. Now, what I've shown so far, these 2 bonds, I'm showing these bonds between 2 atoms of the same element. Because they are atoms of the same element, Dalton's atomic rule tells us they have the same properties. And because they have the same properties, they're going to share these electrons equally. Because they share these electrons equally, these types of bonds between 2 atoms of the same element are defined as a pure or non-polar covalent bond. Now let's look at a couple of heterogeneous bonds. So that's bonds between 2 atoms of different elements. Remember, the octet rule states that the main group elements will gain, lose, or share electrons to form an octet. An octet is 8. There are exceptions to this octet. Now, we're specifically, the octet rule was meant for the main group elements. But more specifically, what we learned is the octet rule, although is a great rule of thumb, is really applies to the row 2 main group elements. So that's where we're going to focus initially. So if I have carbon, and carbon comes in with 4 valence electrons, and we've seen that. We saw that on the initial part of this video. So we have our 4 electrons here. And what I'm going to do is I'm going to create what's called the Lewis structure of methane. So carbon comes in with its 4 valence electrons. Hydrogen has 1 valence electron, and we have 4 of them. So we're going to have a total of 8 electrons around this molecule here. So now I'm going to bring in my hydrogens. Now this hydrogen comes in with 1 electron. This hydrogen comes in with 1 electron, this one also, and this one also. So as you can see, once I pair up these electrons, then what I have done is I have created bonds. So I can take this structure and make it a Lewis structure now without the dots, because one line is 2 electrons. And you can see I have obeyed the octet rule for carbon because all of these bonds are considered part of carbon, so that's 8 electrons. But I have also satisfied the duet for hydrogen. Hydrogen wants a duet because this bond is around this hydrogen, this bond's here, here, and here. Remember, one line is 2 electrons. Now, exceptions to the octet rule include hydrogen, who wants a duet, and boron, that doesn't want a duet or an octet. Boron wants 6. So the octet rule, although a great rule of thumb, isn't too much of a rule, but it is something that we do need to keep in mind as we draw what are called Lewis structures. So let's draw ammonia. Ammonia is NH3. Now nitrogen comes in with 5 valence electrons, and hydrogen comes in with 1, but we have 3 of those for this molecule. So again, we have, that was an odd looking 8, we have 8 electrons for this molecule. Now the steps I'm taking here, the first thing we're doing is we're identifying how many valence electrons we have. And the next thing I'm doing is I'm going to draw what is called the skeletal structure. Now what that means is we need to take a central atom and then we're going to bond our outside atoms to it. Now most of the time the first atom listed is called our central atom. Not always, and I'm going to show you one that's not. But in this case it is. So I'm going to write my nitrogen down first. Then rather than counting dots, I'm going to make my skeletal structure. I'm just going to bond the other atoms to it. Now I'm going to count my valence electrons, and I have 6 used, but I had 8 in my structure. So now I would fill in, so fill electrons on the outside. Then I'm going to correct the electrons on the central atom. So these are the 4 steps we're going to take whenever we create a Lewis structure. Now I've used 6, I've done this and I've done this. I've used 6 electrons. Now I should fill in my electrons on the outside. I have 2 electrons left, but hydrogen is satisfied with a duet and hydrogen will only ever make 1 bond. So hydrogen's done. I need to move on. Now I need to correct the number of electrons on the central atom because I've only used 6 and I had 8 to distribute around this molecule. Then nitrogen is going to get a lone pair. This lone pair of electrons are called a non-bonding pair of electrons. Let's draw water. Water's chemical formula is H2O, and that tells us we have 2 hydrogens and 1 oxygen. Oxygen has 6 valence electrons. Each hydrogen has 1. That's a multiply, not an add. And we have 2 of them. So again, we have 8 electrons to distribute around this molecule. So first, number of valence electrons. We've done that. Number 2, we're going to draw the skeletal structure. Skeletal, there we go. Now, I said most of the time, the first atom listed is the central atom. Hydrogen cannot be a central atom, and that's because hydrogen will only ever make 1 bond. Hydrogen will only ever make 1 bond because it only has that s orbital, and that s orbital is full with 2 electrons. So that's only 1, which equals 1 bond. So it can only bond once. So here is an example where the central atom is not first. So oxygen comes in with its 6 electrons. We have counted the number of valence electrons. So now let's draw that skeletal structure. So I'm going to put a hydrogen on either side. I've used 4 electrons. So now I need 2 electrons on the outside, but hydrogen is satisfied. So now I electrons on the central atom. So I have used 4. Oxygen is going to get 2 lone pairs. Now remember, we want to separate these pairs of electrons, whether they're bonds or they're lone pairs, because they all have the same charge. They want to get away from one another. So we will separate them like this. Now another example, is going to be carbon dioxide. Carbon comes in with 4 valence electrons, oxygen comes in with 6, and we multiply that by 2. So we get a total of 16 electrons for this molecule. We start by drawing our skeletal structure. Most of the time, the first atom listed is called the central atom, and then we bond our other atoms to it. Now I've used 4 valence electrons, so my next step is to put the electrons around the outside. So I've used 4. Here's a pair. There's 6, 8, 10, 12, 14, 16. That seems okay. The octets are around oxygen, are satisfied, but carbon is not. Notice how carbon only has 4 electrons around it. That's not a situation that carbon is going to stand for. So what happens is we have to share more electrons. So this lone pair of electrons, now that we've put our electrons around the outside, we've done these 3 steps, now we have to correct the electrons around the central atom. So this lone pair of electrons is going to come down and make another bond. That's going to happen with this pair of electrons as well. Carbon wants to make a total of 4 bonds. Oxygen, in an ideal situation, is going to want to make 2 bonds, just like hydrogen only wants to make 1 bond. So once we correct this structure, then I'm going to get rid of this lone pair because it's now being shared. Then what we have formed are called double bonds. See the 2 lines here? That means a double bond because there are 2 bonds. Now specifically, and I'm going to name drop again, because these black bonds are my sigma bonds. Sigma bonds are single bonds. The ones that I have in this pink-red color, I can't quite tell what that is. These are called pi bonds. Pi bonds. I'm name dropping that now so that you can get used to it, so once we start talking about how those are formed, you know what they are. So we have these double bonds, and the double bonds will be added in order to redistribute the electrons to satisfy the octet of both the central and the exterior atoms. So now carbon has 8 electrons around it because each one of these lines is 2 electrons. We have 2, 4, 6, 8. And oxygen also has a satisfied octet. Remember, these atoms are part of row 2. They are main group elements, and because of that, they have to obey the octet rule. So we have 2 lone pairs, so that's 2, 4 electrons, and then 2 bonds, 6, 8. So everybody in this molecule's octet rule is satisfied, and this is the Lewis structure for carbon dioxide. We can also create Lewis structures for more complicated molecules. For example, if we have this chemical formula, this is formaldehyde. Now in this case, we have 3 different elements. Most of the time, but first we have to count our valence electrons. Carbon comes in with 4 valence electrons, hydrogen comes in with 1, and we have 2 of them, and oxygen comes in with 6. So we have a total of 12 electrons for this entire structure. Now again, carbon is going to be our central atom. Then we bond our other atoms to it. Now some people may want to go like this, and that's going to be incorrect. There's no way you can distribute these atoms or these electrons and make that work. Formaldehyde has carbon as the central atom. Remember, hydrogen only wants to bond once, so you can't put an oxygen over here. That's not going to work because that's 2 bonds on hydrogen and it doesn't have the orbitals for that. So here we have our skeletal structure. We've used 6 electrons, so we have 6 more to use. Our next step is to put the electrons on the outside atoms, so I'm going to focus those on oxygen because hydrogen is satisfied with its duet already. So now I have used my 12 electrons. Is this my Lewis structure? Well, it is not, because this carbon only has 6 electrons around it, and that does not obey the octet rule for carbon. Carbon is steadfast in obeying that octet rule. So we must share more electrons. So we're going to take these lone pairs of electrons and we're going to drop them down here, form a new pi bond, and that is our Lewis structure. So we have this double bond from carbon to oxygen. Now, just a little brain candy for those of you who may be moving on to higher level chemistry. This is called a carbonyl. So if you're going to be pushing on into organic chemistry, this is very important. So I'm just going to name drop that one a little bit. So this is the Lewis structure for formaldehyde. Now let's draw the structure for ethylene. This is ethylene. It's 2 carbons and 4 hydrogens. Now each carbon comes in with 4 valence electrons and each hydrogen comes in with 1, and we have 4 of those. So we have a total of 12 electrons for this molecule. I'm going to draw the skeletal structure here. I start with carbon in the middle and then I'm going to put hydrogens on it, and this time my carbon is going to be bonded to another carbon. So now I've used 2, 4, 6, 8. I've used 10 electrons, and my next step is to then put electrons on the outside atoms. Well, these elements, hydrogen, they're satisfied with their duet. So now I'm going to move to my central atom, or atoms in this case, and I'm supposed to correct those electrons. Well, if I put a lone pair here on this carbon, then this carbon's octet is not satisfied. So that tells me I must need to share these electrons and drop them down right here and form a double bond between the carbon. Double check that you've used only the electrons that it came in with. We only came in with 12 electrons. So we have 2, 4, 6, 8, 10. We have 12 electrons around this molecule. Everyone's octet rule is satisfied. Hydrogen has its duet. So this carbon has 4 bonds around it. The double bond is actually 2 bonds, a sigma and a pi. So that carbon has 8 electrons around it. This carbon also has 8 electrons around it. Therefore, the octet rule is satisfied and we have a valid Lewis structure. Now let's draw carbon monoxide. Carbon monoxide, we come in with 4 and 6 valence electrons. We have 10 electrons, which initially students just don't think they can do 10 electrons, but it works. So first we draw our skeletal, well, first we count the valence electrons. Then we draw our skeletal formula, our skeletal structure here. Then we're going to put electrons on the outside. Well, how do we know which is the outside? Well, they both are in this case because there are only 2 atoms. So let's fill it in. So we have 10 electrons. We have 8 electrons left. And if I put them here, 2, 4, what if I put 4 over here, 2, 4, then I've used 2, 4, 6, 8, 10. I've used all of my electrons, but neither of them have a satisfied octet. Well, what happens is we need to share electrons. So these electrons are going to drop down, and so are these. And what we do is we're actually going to form 2 pi bonds here. When we form both of those pi bonds, what we're left with is called a triple bond. And that triple bond is made up of 2 pi's and 1 sigma bond. And that sigma is black, and the pi bonds are pink or red. I'm not sure what color that's supposed to be, but they are not black. So we have our sigma bond here and our 2 pi bonds. Now, each of these atoms also has a lone pair, and this actually imparts some pretty interesting chemistry for carbon monoxide, but this is the Lewis structure for carbon monoxide. Using the same steps, we can also draw a Lewis structure. No, the 2 doesn't go there. We can also draw a Lewis structure for an ion. Now, because some of our polyatomic ions are covalently bonded within the ion itself, it just acts as a single unit. We have covalent parts that are ions. So if we have this is called formate. And carbon comes in with 4. We follow the same steps. Hydrogen comes in with 1. Let's add those together. And each oxygen comes in with 6. So what do we do with this charge? Because originally here we have 5 plus 12, that's 17 electrons. And then we have this charge. We have to take that into consideration as well. When we have a negative charge, that means we have one more electron. So we have a total of 18 electrons around this chemical formula. So the steps are still the same. We count the valence electrons, don't forget the charge, and we draw our skeletal formula. Again, the atom comes first. It's going to be the central atom. We have 2 oxygens this time, so we're going to put them out like that. Now we're going to work on the electrons on the outside atoms. Well, hydrogen is satisfied with alone. We've used 6 electrons, so here's 2 more for 8, 10, 12, 14, 16, 18. So on first inspection, hey, looks done, but it's not because carbon's octet is not full. Carbon needs a full octet. So we have to share. So what I'm going to do is I'm going to take a lone pair from either one of these oxygens, it doesn't matter to me which one you take, and drop it down here, and I'm going to make a pi bond. So when I do that, then we have our full octet. Each atom is satisfied as far as the octet rule is concerned, but you're not done drawing the Lewis structure. We have to put it in square brackets and give it a charge. So that's how we show an ion with a Lewis structure. So this is formate, and again, formate, we have a sigma and a pi bond from carbon to oxygen. That's called a carbonyl. If you're moving on, that will become important. We have a single bond to oxygen that has 3 lone pairs, and then we have a single bond to hydrogen as well. Most of what we've been working with so far have been carbon, hydrogen, oxygen, maybe a little nitrogen. But there are some exceptions that we have to keep in mind. And the carbon, oxygen, nitrogen, they tend to follow the octet rule. But if we have something like nitrogen monoxide, nitrogen comes in with 5 valence electrons, oxygen comes in with 6. We have an odd number of electrons, but we know nitrogen monoxide exists. So let's follow the steps here. We've counted the number of valence electrons. We're going to draw our skeletal structure. That's okay. Let's put the electrons on the outside atoms. Well, we only have 2, so they're both outside atoms. We've used 2, we have 9 left. So here's 4, 6, 8, here's 9. So nitrogen isn't even close to having its octet satisfied with this arrangement. So I'm going to drop electrons here, and I'm going to drop electrons. I'm going to drop 1 set of electrons. And when I do that, make this pi bond here. Erase this because now I've used them. Oxygen still has its octet satisfied, and now nitrogen has 5. It came in with 5. This is the Lewis structure for nitrogen monoxide. We do have an odd electron, and that's a strange thing to have, but it does occur. And we actually call this a radical. You will move into free radicals if you end up taking organic too, but radicals do exist. Another exception are deficient atoms. For example, when we have boron, and if we're going to make boron trifluoride, boron comes in with 3 valence electrons. Fluorine comes in with 7. So 7 times 3, that's 21 plus 3. We have a total of 24 electrons here. We're going to draw our skeletal structure for boron, and it's going to look like this. Then we're going to put our electrons on the outside atoms. So now we've used 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used all of our electrons. And all of fluorine's octets are satisfied, but what about boron? Boron only has 6 electrons around it. So do we share? Do we drop and create a pi bond? And the answer is absolutely not. Boron is satisfied with its 6 electrons, and your halogen will never, halogens do not make double bonds. Halogens will only bond once. So we have this for our Lewis structure for boron. So this is called a deficient atom, and it's satisfied to have its 6 electrons, and this is how we draw it. Now, there is experimental evidence that actually shows that there's some double bond or pi bond character between these, but it's not drawn. So we're going to keep things focused, and we're just going to leave them as single or sigma bonds for our Lewis structures. And then the last of our exceptions are called hypervalent atoms. Hypervalent are also called expanded octets. So if we expand an octet, it's more than 8. And that only happens after row 2. If you're looking at row 2, it will only have a maximum of 8 electrons because it only has that s and that p orbital, and together they can only hold 8 electrons. So some examples of some hypervalent molecules, if you have phosphorus pentachloride. Phosphorus comes in with 5 valence electrons. Each chlorine has 7. So we have a total of 40 electrons here. Again, we draw our skeletal structure. Skeletal structure like that. We add in our electrons on the outside atoms, and then we have the Lewis structure. Now, there is no correction I need to do for this central atom, and we have used all 40 of our electrons. Phosphorus is an example of a hypervalent atom. It can go more than 8 electrons around it, and that's because of the orbitals that are available to it. Another example of an expanded octet, sulfur hexafluoride. Sulfur comes in with 6 and with 7, and we have 6 of them. I just put that in the wrong order. So there's a total of 48 electrons to be used. Just like before, we draw our skeletal structure, and we fill in our electrons on the outside atoms first. There is no additional correction that we need to do for the central atom. Sulfur is another example because it's in period 3. It can expand its octet. It can hold more than 8 electrons and bond more than 4 times. And the last of the hypervalent examples I'm going to show you is xenon tetrafluoride. Xenon is a noble gas, but it can also make fairly stable structures. So xenon comes in with 8 valence electrons. Each fluorine comes in with 7, and we have 4 of them. So we have a total of 36 electrons for this structure. We draw our skeletal structure, so we have xenon, and we have our 4 fluorines here. And then we put our electrons around the outside. And now we've used 4 times 8, or 32 electrons. If you have extra electrons and your outside atoms octet are satisfied, then they go on the central atom. So in this case, xenon is going to have 4 bonds. It's also going to have 2 sets of lone pairs. So again, the exceptions to the octet rule, and we like to say the octet rule is the way to go, but the reality is H wants a duet. Boron is happy with about 6 electrons. Carbon, nitrogen, oxygen, they're the ones that want the 8 electrons. Carbon is going to want to make 4 bonds. Ooh, bonds. There we go. Nitrogen is usually going to make 3 bonds. It's possible for nitrogen to make 4, but it usually wants to make 3. Oxygen wants to make 2 bonds. Now the halogens, which I will just represent with an X, the halogens also want 8 electrons. They will make a maximum of 1 bond. So when we can have an odd number of electrons in our molecule, we call those radicals. They do exist. They're going to be few and far between, at least in general chemistry. We also have deficient atoms, specifically something like boron. That's going to be deficient. And then we can have our hypervalent. Our hypervalent is going to be called an expanded octet. And that's not going to be in period 2. That's going to be in period 3 and beyond.